Hello, thank you for attending my talk. This is pre-recorded a month before the conference. I'll be speaking about electrofacies and improving geomodels. And I would like to acknowledge three companies here that have provided me with technology that was used in this for material in this presentation. The agenda for this talk is shown. We're going to go over some geomodeling context, a bit on facies themselves, definitions, classification and why we're doing this, and motivation, a little bit on concepts, just to give you some flavor for the background and issues to address. And then we're just going to take small pieces of some case studies and show you some examples. Finally, we'll just comment on geomodeling impacts and then summarize the process. Okay. So the goal here is ultimately is to bring consistency to facies logs used in modeling, thus enhancing the workflows, integration of data, and quality of reservoir models. The premise here in this talk is that the facies logs we use for modeling are typically not tuned optimally to the hierarchical geomodeling workflows. So I will explain further. So geomodeling involves concepts to models. What we have here then is a diagram of, say, an outcrop or a picture of an outcrop. And the sedimentologists will look at these analogues. They'll interpret facies. From that, they will identify depositional environments. That leads to the stratigraphy, understanding the stratigraphy. With that information, concept models can be developed, and those concept models very much guide the geomodeling process. So these concepts drive modeling, they drive the interpretation of the logs, core logs, images, in order to get facies logs going into models. So we're after this whole data integration process, and it's really based on good quality logs and concepts. When we look at the context of geomodeling, we work with a variety of data. It's multi-scale data from core, logs, to models, to even upscaled or rescaled flow models, seismic, for example. And so having a strong, consistent facies log input to the process improves our scale changes and our model integrity. In geomodeling, facies are used as hard conditioning data, and they're used to represent and honor reservoir heterogeneities. So the facies combined with petrophysics are the heterogeneities. First of all, the facies allow us to model reservoir architecture described by that sequence of lithofacies, and then within those facies we get that variability of the rock properties. So facies are used as a hard data, as a truth data, if we want to call it that, and within them we have these domains of properties to model. And so 1D facies are significant data type in the subsurface workflow. Let's quickly go over some definitions so we're on the same page. We got practitioners from different disciplines describing the facies from their viewpoints. So facies is really describing the face of a rock, and it's just a general term. Lithofacies is describing the characteristics of a real rock. It's typically described during visual inspection of the actual sample, looking at trying to visually inspect properties. Biofacies and ichnofacies describe biological content of actual samples through visual identification. which supports differentiation of depositional environments. You'll sometimes hear people more commonly use the term depo-facies. Electro-facies is a term describing log-derived lithologies or rock types using statistical methods. These are multivariate methods. Petrofacies is just a common term using log-derived lithologies or rock types. And rock types is the engineering term. There are advantages to using electrofacies technology. It is underused, but it does provide a robust framework of methods. So it improves integration and consistency in the application of well data for conditioning in the geomodeling workflow. It strengthens the geology to flow principles. And the idea is that it decreases observational bias in facies classification. It decreases facies uncertainties, and it can be an enabler for faster runtime in the geomodeling. And potentially it could reduce the need for coring. There are barriers to adoption of electrofacies. The workflow steps are not widely established in our industry or promoted by the software vendors. And there's definitely a lack of best practice guidance and training. And there's misuse and suboptimal application that sometimes creates barriers within companies. There's a lack of dissemination of the software within G&G groups to staff beyond petrophysicists. And this holds back the technology because it needs more than just petrophysics. So we need to treat electrofacies as a practice that's open within the team. It's driven by interpretation. It's a guided machine learning process, methods. So electrofacies, the general idea is that we have some identified observations. There's facies named, identified. We have new samples. So here we have density gamma. We've got 2 new samples. And we want to find which facies these new samples belong to. So really the idea is that we have these clusters, and in a single variable we don't discriminate them. It's difficult to separate the modes. So if we look at some rotation and get a discriminant function line, we find an orientation in space where the 2 clusters are separated the most and inflated the least. So this is really a parametric method with the class covariances are minimized and the between class covariances are maximized. That said, we can look at other terminology. There's centroids, which is really the center of mass, like the mean is to a histogram. And we can look at different sizes and distributions of shapes. So giving an example of a quick example of an unsupervised method using a handful of wells and 3 variables. The densities, the high density areas are identified and seeded. So we've got a binary facies system, and we're going to apply a classification, classify all the samples. Oh, we might have gone to 3 clusters, but here we have 2 binary facies. And then we looked and see how it's behaving. Well, that was using 3 variables. Well, porosity is computed from 2 variables and electrofacies from 3. Here we have the binary facies, and we have a net, non-net, let's say. And then porosities, I've color-coded it or color-filled it, illustrating how nicely it matches. So we have this petrophysical consistency just in a simple classification. Whereas a single variable like V shell, derived from gamma, does not discriminate well enough to use as a facies. So we need to be working with these multivariate. We're going to skip the assumptions behind discriminant analysis because we don't have time, but they would be an important additional topic. Electrofacies modeling as an approach has different methods. So there's the unsupervised, which we gave an example of, and then supervised is using the training data. So we showed the discriminant analysis whereby we find a function to separate the clusters. But if we look at non-parametric methods, first thing is that our data it has some complexity to it. And so the parametric approach doesn't necessarily capture the complexity of our actual training data sets. So we do need the non-parametric for our facies interpretations. In this example, or in this slide, we're referring to Bayesian classification. There's also neural networks. But here, the way this is set up is just saying, for a given observation, what is the probability that it belongs to a particular facies? And then we solve for that. This slide is from a North Sea study, and it really illustrates the moving parts in the process. So first of all, we have the training set, which shows 3 logs, gamma, density, neutron, and our training facies, which has been cleaned up. That's another topic on cleanup. We then have 4 facies, and we come up with 4 probabilities. So the probability of occurrence of each of the facies, it's that maximum probability that gets assigned to the final maximum likelihood facies, and which is shown here. And so in this zone, we have high probability of the yellow. In here, we have a high probability of blue and red. And notice when we compare to the training set that the output facies, electrofacies, has a different level of heterogeneity, consistent with the. In this carbonate reef example, it's just a summary. In this study, actually done 20 years ago, we only had about 10% core coverage. So we also had distinct facies in the forereef and in the lagoon, different energy depositional environments, and it's important to have different petrophysics associated with different porosities. At that time, a lot of people just use porosity to model carbonates. Having the facies allowed us then to classify facies over different areas and have trends in our facies, have different permeabilities, like higher vertical perm in the higher energy environment for the same porosity magnitudes. Okay, so then here's another example. It's just showing cleanup. So with a large number of wells, we have a lot of overlap. We had a high density stringers here with some, either misclassification or bed boundary effects, core shifting, things like that. So we applied a heavy cleanup. So this is not an unbiased process. We have to clean up the data based on geologic knowledge, and then we use this as in the training set. And so there we get the final result. What this did was it really improved the petrophysical information and the match of the facies petrophysics going into the modeling process. That's porosity, permeability, and the saturation. So a last point to make on this example is the comparison of the electrofacies models when we got some new data and used the new data as a validation set. The sedimentologist I was working with had identified that the earlier electrofacies model did not quite capture this lower short face, the slightly degraded quality sands. And so we adjusted the model ever so slightly to increase the proportion of the more degraded facies. And this was basically a guided process to match sedimentology and our concepts. And so it's very much a part of the electrofacies modeling, and it improved the workflow. And you can imagine this would slightly change the pore-perm relationships and the flow through this section of the model. Here's an example that was presented in New Orleans. It's just illustrating the facies interpretation, visual interpretation of this point bar deposit, and it's rather coarse. There's a lot of variability in the logs, and it's a larger scale facies interpretation based on core and image logs. The electrofacies illustrate a more variability, more consistency with the logs. Here we have another well from the same field study, and this one illustrates the same change of scale when we go to the electrofacies, more variability, but it also has the image logs, and there's quite a consistency between the variability in the image log and the electrofacies. Let's consider blind tests. It's good practice to use them. Maybe withhold some wells, or use new wells to check the models. So first of all, the concept facies are mainly defined by the percentages of mud visually in the clastic. So that'd be like the V-shell range. That's a driver for that. And some textural issues are used for the interpretation. Now, classification errors tend to be a regrouping to an adjacent facies in the process, and that's not always a bad thing. That can be a good thing, because there are bed boundary effects in the given interpretations, and core shifts and things like that. Finally, breccia is a textural type facies. It is a challenge to classify it correctly, but it is also broadly interpreted with small class to mini class. Breccia is sometimes a catch-all. Let's look at the curves that we're using. So here, density, gamma, neutron are three base curves. They're very good curves to use. Sonic, when we have them, is very helpful as well. It's very good for, it really improves the classification of breccia, for example. Photoelectric can be helpful, although it does need to be checked for some normalization issues, just as gamma ray needs to be checked. And then finally, the shear sonic, it's a little less helpful because it's a lower frequency type measurement, but it can contribute a little bit. There's a lot of topics. This is a big subject, and there's a lot of topics we're not going to discuss. Here's a comparison of the electrofacies model using the different numbers of curves. First, we have the visual input facies in the training set. And again, it doesn't have the variability of the log scale. So what we observe is that each of these models actually has variability that would be quite useful for giving us consistent facies and log properties in our modeling. Here are three wells also used for blind tests. They were new wells. We're looking at a non-net well here, and note that the visual facies are, the overall pattern's similar to the electroface, but the electrofacies is regrouped based on some quality considerations. In this well, this middle well, this is a net well. There's a massive sand interpreted here, and yet the electrofacies have regrouped to adjacent quality sands that are still net to almost non-net. So this would have a direct impact on the permeability model and the sweep efficiency in this area and how we build our models. Then this last one, this third one, is kind of a marginal well, and it's really quite consistent between the visual and the electrofacies model. So we've discussed improving the variability of the facies and its consistency with petrophysics. When we build petrophysical models, geomodels, we get that relationship between porosity and permeability and KV/KH. Now we can have a more sophisticated model. This shows the nonlinear relationship of poro-perm and the percolation effect of the vertical to horizontal permeability. That is, that the flowability of the rocks doesn't take off in the vertical until we get to the higher quality facies. This is important to the flow. As well, in the water saturation, when we look at it by facies, we can now fit these trends, elevation trends, and use them in the modeling process. And this helps us capture that transition effect at the bottom, whereby the best quality facies have a sharp transition, and as the quality degrades, that transition steepens. So we're capturing a strong capillarity effect, which improves the flow modeling in the simulator. As well, we could even estimate the irreducible water and improve the engineer's use of RELPerm. So in summary, our motivation to improve the facies has to do with generating improved, reliable inputs to our geomodels. What we're after is improved quality, accounting for misinterpretation, bed boundary effects, depth errors, things like that. Also coverage. So we're getting a facies log in uncored intervals or uncored wells. Then finally, we have an improved consistency with petrophysics. This improves model fidelity, the sharpness of the models. So electrofacies as an application can also be used to improve analog field studies and applying the same model in the analog fields if we want to compare to assets. Finally, this accelerates our subsurface projects by allowing us to get into the modeling sooner and better, and improving even the simulation work, the flow simulation, and improving our decision processes. So we're after modeling heterogeneities. Let's define the most important ones.